Good morning, everyone. On behalf of EIT Bhopal University, I welcome you all to today's lecture, which is going to be delivered by Dr. Debi Prasad Choudhary from California State University. EIT Bhopal University is celebrating National Science Week during 22nd to 28th February 2021 to commemorate the discovery of Raman effect by the great Indian physicist Sir C.V. Raman. Today's lecture, we have our distinguished speaker from California State University, Dr. Debi Prasad Choudhary. Dr. Choudhary completed his PhD degree in 1990, working on high-resolution spectroscopic study of comets. His postdoctoral work has carried out at Max Planck Institute, Germany, where he used large telescope at Keller Alto, Spain, to study the Jovian plasma torus. He has been studying various topics in solar astronomy since 1992. He was awarded the Research Associateship of National Research Council for 2 times in 1998 and 2003. In 2001, the National Astronomical Observatory of Japan awarded him the Center of Excellence Fellowship. He is a member of several professional associations such as American Astronomical Society. He is a member of American Geophysical Union and American Association for Advancement of Sciences, Astronomical Society of India, and International Astronomical Union. So at this juncture, I'll again welcome Dr. Debi Prasad Choudhary to this platform. It's over to you, sir, please.
Yeah, thank you. Thank you very much, Sarath, for inviting me to give this talk. And okay, so let me share the screen. Yeah, I hope you are able to see the screen. When Sarath invited me to give this talk, he suggested a topic, of course, to talk about the spectrographs in the space, and we have been using these instruments. I have been using for last several years, and I thought that kind of a topic you can hear from other people, and I was happy to see that Ayuka, I think Durgesh gave such a talk where he's talking about the instrument that is being built in India for the solar observations from the space. But I wanted to talk something more basic that is related to Sir C.V. Raman, and that is the instrument that he used to discover his this effect, Raman effect, and his association with Mahatma Gandhi. And I selected this topic. I actually suggested him, and I'm happy that Sarath accepted that suggestion and allowed me to talk about this topic. But at the same time, I must confess that after I suggested this topic, I found it was not that easy to put together this talk. I had to do a little more research to find some more stuff. But basically, I wanted to talk about this because, a couple of years back, I was going to, I was, redesigning our senior advanced physics laboratory for our seniors. And I had a lot of these experiments like Michelson interferometer, spectrograph, and some other instruments I had. Already these are all there, but then I thought, since I am teaching this lab, I should include Raman spectroscopy. And then I was looking for an instrument to buy to do this Raman spectroscopy for the students, and I found that this instrument is pretty expensive. The cheapest one is about $100,000 you can buy, and of course more and more you pay and better instruments you can buy. So, and that kind of money we didn't have for the students. Then I thought, Raman discovered this effect 100 years back without any money at that time, and why can't we set up a lab with simple spectrograph the way Raman did. And so I gained a lot of interesting facts about Raman's own experiment and his association with Mahatma Gandhi and so on. So I became fascinated with Raman's life. Of course, when I was a student at PRL, Physical Research Laboratory in Ahmedabad, those days we used to have two students of Raman teaching us, Ramanathan and Pisharati, and I had association with them, but I was not so much um, trying to understand how Raman did these research and so on. But this was an opportunity that I used to learn more about Raman and people of his time, how they were motivated and how they were doing science. And I think at this time it is it is still a it's still an active kind of attitude we should have to progress in science. And in that process, I found that Raman, before his death, before actually one day of his death, before one day of his death, he says this powerful statement he makes, that I believe only in spirit of man. I have heard of godly men like Jesus, Buddha, and I have met a godly human being, Mahatma Gandhi. That was one day. He died on 21st of November 1970. And before one day, he tells like this. So then I became quite interested to know why he was so much, respectful and adoring Mahatma Gandhi. So I'll just tell you a little bit things that I have. So basically, as I told you, the purpose of this talk is that why these two people, that Mahatma Gandhi and C.V. Raman, I wanted to discuss at the same time. Why? These two people? Because these two people were both interested in original stuff, not influenced by external factors. Like Mahatma Gandhi was not interested if people abroad respect him or like his work or things like that. And same thing, C.V. Raman was more to the basic fundamental truth, his passions for pursuing truth. So these were both original people, not influenced by external factors for what they were doing. And they were very kind of passionate about their fellow man, that is patriotism. So to show, actually, you will see at some places I will show you that Raman says that, there is a very interesting statement that Raman made, which was told to us by our professors in PRL when I was a student there, that if you read a paper, research article, you consider that it is wrong, and if especially consider it is wrong if it is a British author. That was what Raman used to tell his students. Not that all the time you will find this is wrong, mostly they will be correct, but once you discover it is wrong, then you actually make advance in the field. So that was what C.V. Raman used to say. And Mahatma Gandhi's statement, if you see, he says at various stages that let all the thoughts come from all sides. Like, I will open my doors and windows for the thoughts and ideas from all over the world to come, but I will not, those thoughts will not shake me. I will have my own thoughts and I will do what I consider best. So that was what Gandhi's idea. And these are all parallel kind of, they take ideas from all around, but stick to what they think is correct. So, so these were the factors that motivated me to kind of think and discuss these two individuals in the same platform. And in this lecture, actually, this lecture is quite difficult, as I told you, because I have never given a talk on non-science or little bit less science like this. Usually, I give talks, on technical talks like astronomy, radiative transfer, comets, and things like that, solar flares, magnetism in the sun, and so on. And those are all structured and known facts. But here, I am trying to basically deviate from my usual practice and talk a little bit on the social aspect of the science also. So it is first time I'm trying, and just bear with me. So, and in this lecture, my goal is not to impress upon you that Gandhiji liked science or how much he knew science. That is irrelevant. That is not what this lecture is all about. I would like. I'm interested in this lecture to understand why Mahatma Gandhi was adored by great scientists like Raman, Einstein, and how they were inspired by him. So, Gandhiji knew very little science. He was not trained as a scientist. He was a barrister, a lawyer. But so my goal is to find out why Gandhiji was adored by these scientists like Raman. Raman was a very proud man, and he would, not. I have heard from his students that his students were terrified by him. He, there is a story that in Raman Institute, one of his on one of his birthdays, they wanted to give him a bouquet of flower, and they were all afraid. So they asked a female student to make a bouquet and give him, and all these other students were behind her, and they were once the plan was that once she gives the flower, and rest of the students will say happy birthday, sir. So they went to his house and they gave the flower, and then first thing he asks is, where did you get these flowers? Is it from the institute or from somewhere else? So he was like that, and he will not, he was not that kind man, but he had a very soft corner for Gandhiji and respected to the highest possible respect, adoration that he had for Gandhiji. So I want to know why. So, okay, this lecture is divided into two parts. First half, I will describe the Raman effect and how Raman discovered this effect, and about the spectrograph that he used a little bit. And then the next half, I will describe his association with Mahatma Gandhi. So this is actually this left side is the instrument that you see. It's a wooden instrument. Is a spectrograph where you have a prism in the center, and the light sort of goes from here, and then it is the prism is at the center, and you see there is eyepiece here, and you will see the dispersed light this side. So that is the instrument he used when he was working as a professor in Calcutta. But later on, there was, as you can see, the right side, this instrument was a little improvised instrument, but still, in the present standard, it is very rudimentary. Actually, I have one in my my home where you can actually see the spectra through a telescope, And this side, you have the light source. So the light source comes here, and you have the dispersing element at the center in this box at the center. It may be a grating or a prism. And basically, he used a quartz prism for Raman effect, and I'll tell you why quartz prism is required. And then you can see through this the spectra. So initially, he uses this instrument to see the spectra, and then that led to the discovery of the Raman effect. So what is Raman effect? So Raman effect is basically scattering of light. So you have, you have material from where the light scatters, and when the light scatters light, today you know that these are all electromagnetic, you can consider them as electromagnetic waves or photons. And those are, these particles, let us say photon particles, are scattered by the molecules or molecules or atoms. So they scatter light. And when they scatter light, there are two kinds of scattering that can happen. One is the elastic scattering. Elastic scattering means, I guess here you have a cartoon in the, yeah, here you have a cartoon which shows that you have a dye, a water molecule, let us say. This is a oxygen and hydrogen, two hydrogens, water molecule. And the molecules, so atoms have ground state and excited state. That is, atom can be in the ground state when all the electrons, they orbit the nuclei in various orbits. These energy levels or the orbits are decided by the quantum mechanics, and quantum mechanics allows the electrons to be in certain discrete orbits only, not in between. So that's why when a hydrogen atom, for example, emits, it emits at fixed wavelengths. So that is how an atom is designed. That is, at the center, you have the nucleus, and around the nucleus, you have these orbits in which electrons reside. And depending on the energy, it will be either at the ground state or in the excited states, depending on the energy of those electrons. Now, when you have a molecule, there are other things that happen. It is, of course, it will be there like this, that you have, for each atom, you will have a nucleus and these orbits, but at the same time, since this is a complicated system, they will have rotation, because there will be a axis of symmetry around which the molecule will rotate. This is the, suppose this is the axis which around which there is a symmetry, then around this the molecule can rotate, or molecule can vibrate. For example, along these rods, there are no such rods, real rods, but you can consider them as the bond. So along these bonds, the molecule can vibrate. So what happens actually is that when the photon is absorbed by the molecule, then the molecule, the electron cloud around the molecule will be polarized, and there will be the energy will be redistributed, and then there will be a when the molecule goes to the ground state, you will get another photon that will come out. So in practice, what happens is that when the light enters a system, then the atom or molecule absorbs it and radiates it. And sometimes the same photon that is absorbed by the molecule or the atom comes out, and that is known as the elastic scattering. That is the same, the wavelength doesn't change, or the energy of the photon doesn't change. So this is, for example, the blue photon, green photon goes in and green photon comes out, and that is elastic scattering, and that is known as the Rayleigh scattering. And the sky is blue because of this, that the sunlight is scattered by this kind of a mechanism that is called elastic scattering. And but the Raman scattering is inelastic scattering. So a small amount of light is absorbed by these molecules and transferred to the vibrational, rotational, or electronic energy of the molecules. And then some energy is lost, and then the photon comes out at a lesser energy. So here I saw in the left side, you can see this energy level. And so you have this ground state, and these are excited state. So the incident photon takes the electron to the excited state. And when this comes to the the de-excited state, when it is less, these are known as the Stokes scattering, and anti-Stokes scatterings are when the energy is more. So sometimes in the inelastic scattering, the photon will lose energy into the system, or it will gain energy from the system. If the molecule is already in the excited state, then the photon will gain energy, or the light will gain energy, and then you will have a photon that comes out at a higher energy. So the Raman scattering is basically an inelastic scattering in which the incident photon gains or loses energy. So that is what is the Raman scattering. But then the efficiency of this inelastic scattering is very small. It is 10 to the power minus 7. 1 in 10 to the power minus 7 photons will undergo this inelastic scattering. So it is very difficult to observe. That is why the instruments are so expensive. So otherwise, the elastic scattering, actually you can see with a simple spectrograph, but for detecting the Raman effect, you need actually a powerful light source and a powerful spectrograph, and that's why the cost goes up. And I'll tell you a little more. So a little more about this Raman effect. The classical, at that time when Raman discovered this, it was 1920, in the late 1920s. And at that time, the quantum mechanics was not there. So this has to be explained by simple classical electromagnetic theory, and which means that, so the polarizability. So the dipole moment P is induced to the molecule, as I was explaining you in the previous slide, by the external electric field. So when a electromagnetic wave enters into the molecule, then the molecule will have a polarizability, that is the electron cloud around the. So this is a neutral species. For example, a molecule, you have all the electrons and protons, positive and negative charge, completely uniformly distributed, then you will have a neutral species. But if you separate, say for example, to this neutral species, you take a positive charge, then ion, for example, you take, then the positive and electron cloud, positive charge and negative charge will be separated. And so this, at this state, the system is known as polarized. And this polarizability is basically proportional to the external electric field, and this alpha is the proportionality constant. Now, depending on the molecule, this proportionality constant changes. Some molecules are more polarized, easily polarized, and some molecules are not so easily polarized. And so basically this vibration and rotation state of the molecules can be detected using Raman scattering. And that is because this polarizability of different molecules and different states of those molecules are different. So Raman scattering occurs because molecular vibration can change the polarizability, and the change is described by the polarizability derivative, that is d alpha by dq, and q is in some coordinate system. And so basically you have to have dq, d alpha by dq non-zero. That is it must be a molecule, and that molecule should be polarizable. That is, if you incident light, it should get distorted. That's why only molecules will display this Raman effect and not the metals. For example, you take iron rod, you will not see Raman effect. So basically, that's what we show to the students, that you take a thin film, for example, thin film where you have all these molecules that are coated onto a glass, and then you see the Raman effect. But you take a metal sheet, you will not see the Raman effect. And actually, this semester we had graphene sheet, and you incident light, and you will see the Raman spectra. And so this is what Raman did, that you have a prism, and actually those days there were this intense light source was not there. So what he did was he had a ciliostat, and he used to reflect sunlight and guide sun so that the sunlight enters the lab. And then you have these, through a prism, you can actually see all these colors, red to violet, violet to red. You can see all these colors. Blue to red is actually our eyes can see only from blue to red. But violet and infrared you cannot see. But it's, little bit towards violet you can see, but not much. And our eyes are sensitive to blue, 4,000 angstrom to 7,000 angstrom, that is, or basically 400 nanometer to 700 nanometer. So only this range is sensitive to our eye, and that is because that is another story. It's not related to this topic, but we can see in this wavelength range because we are in the neighborhood of the sun, and sun is a yellow star, and a yellow star means the maximum light sun produces is in yellow color. That is because the surface temperature of the sun is basically 5,800 degree Kelvin. At that sun, if you consider sun as a black body, it will emit light from blue to red. And the maximum light comes in this wavelength range. And since we are evolved around this star, our eyes are sensitive to this star, this color range, basically. But anyway, this is from, you can disperse light in this wavelength range. And then so what Raman did is that this light he filtered so that only violet light is allowed. The other side, he uses a filter to allow the violet light. And violet light, because if you do the analysis, quantum mechanical analysis of the Raman effect, you can show that the Raman scattering is the efficiency of Raman scattering is more in shorter wavelengths, that is violet, blue and violet wavelengths. The scattering is more efficient. So he separates to violet wavelengths, and then he has a liquid right here, and then this liquid absorbs this light and scatters light all around. Actually, this Raman scattering is isotropic, it goes all around, but in one direction you observe. So in this direction, all this violet light is scattered, and also some light which is in the green, that is lower wavelength, higher wavelength, means lower energy, is scattered. So these are the two lights that means in the big, what he did is he blocked all the light and only allowed violet light. But when it came out both violet and green. And at that time, how do you know? Because you can actually stop this with a green filter. You can stop violet and only let green light pass through. And he had a observer. He had students. K.S. Krishnan was one of the great students he had, and in New Delhi you have a K.S. Krishnan Road, because he was one of his best students. I think he did most of the observation through the eyepiece, eyepiece of the telescope, eyepiece of the spectrograph. He kept on observing, and you could actually see some very faint green light that came out. And that is because he was using sunlight without any focusing or anything, just the scattered sunlight, and then he was observing this. So they used various different types of liquid, I think 200 types of liquid, and then found that in each of those liquid, you can see this scattered light, which has a lower wavelength, which has a higher wavelength and lower energy than the incident light. And so he reports this in Nature, says that this is a new light phenomena. And those days in 1920s, the scattering of light was a very big subject. A lot of people were studying, and Lord Rayleigh had his famous theory, Rayleigh scattering. So most of the elastic scattering that happens without losing any energy, those are in the Rayleigh scattering range. So that light was anyway coming. That was known that will come. But this light, which was due to the inelastic scattering, that means the photon had lost energy, and that is how you get this green light. And so which substance will show this? The sample must have polarizability of electron cloud in the molecules. So that is one. That is, it should not be a symmetric like an atom, but it should have polarizability. And that's why you can take this. The utility of this today is very big. Raman would not have believed that his discovery is of so much use. And Raman spectroscopy today can be used to probe the chemical structure of the material, and so that a lot of information it will give: the structure of the material and chemical structure, and polymerism, and the strain in the stress and strain in the structures, and you can take a trace amount of elements and then find the contaminations or impurity. So these things can be done using Raman spectroscopy. So typically a Raman spectra is a distinct chemical fingerprint for a particular molecule or a material, and can be used very quickly. Means because it is just a non-destructive process, you can use this very quickly to identify what material it is and how it is distinguished from others. So for example, here you have methanol and ethanol. This is the chemical structures are slightly different, but the spectra is completely different. So basically, you can use this as a fingerprint of all these molecules. And but it is not that easy, of course, because you take an unknown material and you will have some spectra like that, and how do you know this is ethanol spectra? So what is done today is that if you go to the website of National Institute of Standards in Colorado Boulder, they have a website where all the spectra are kept there. Spectrum of all the elements, all the ions at various excited states and so on, and all the molecules. So there is a library of all these molecules, and you have your observations, and you match with all these different spectra and find the best match. And it is like, you have a library of fingerprints, and when you come to the United States, they take your fingerprint and they match. They have a library of fingerprints, and if you, depending on how it matches, they identify who you are and that type of thing. So that is how the Raman spectra is used. Now, what use? There is a whole lot of use that is used. Raman can be used to analyze many different samples in general, suitable for analysis in solid, powder, liquid, gel, these rocks, for example, rocks you can take, and in our university, there are some geologists, they use this Raman spectra to identify the minerals in the rocks. And of course, chemistry, they use all the time to do inorganic, organic chemistry, biological materials people use, and are general. These are not suitable, as I told you, for metals or alloys. So if you take a metal sheet, it will not show Raman effect. Only these molecular things will show Raman effect. So so in art and archaeology, because their non-destructive techniques are very important. You cannot take a paint of, say, Mona Lisa and then try to see what is there, what layers are there behind. So that you cannot do. So you use basically Raman techniques to find the pigments in those paintings. And gemstones you can actually characterize. If you go to Surat, for example, they have these, they make diamonds, and they use Raman spectra to characterize how good, what is that gem all about. And carbon materials, as I told you, nanotubes, and I have now acquired some graphenes. Those are used to characterize all those carbon nanotubes or distortions in graphenes and so on. And chemistry, geology, chemistry, purity of the material, geology, as I told you, minerals, they identify, and life science, cells, tissues, drugs. For example, aspirin is one of those drugs which we use in our laboratory to demonstrate, and pharmaceutical use is like that, and semiconductors also in the semiconductor industry. So Raman spectroscopy is used to get the purity of those alloys like gallium arsenide or cadmium telluride, mercury cadmium telluride. Those materials are used to make detectors, and you can actually use Raman spectroscopy to measure the components that are there in those compounds. So as you see, Raman spectroscopy today is used in varieties of fields, and in all these fields, they are not physicists, they are of different background. So for them, this getting the spectra, matching the spectra with the molecule, and all these are there in one package. That's why the cost of the instruments go very high. So here, okay, so let me show you a little more about his instrument. And here you can see Raman with this spectrograph. It's a very simple spectrograph. Actually, in your lab, undergraduate lab, you might have already seen this kind of lab instrument. But he was so excited those days to have such an instrument, and to all the students, he explains enthusiastically about this instrument. And today, this was the instrument that Raman had. And today, the instruments are like this. In the right-hand side, this instrument that you see is full of sophisticated optics, and then detector system. So basically here what happens is the light comes from here. You need to have okay, so before I come to this one, this instrument, if you go anytime to Bangalore, you should visit Raman Institute, and there is a nice museum of all these Raman's Nobel Prize you can see there, and you can see this instrument there. And what he did when he came to Raman Institute in Bangalore, by that time, even though he had already discovered the Raman effect, he was using this for various other advancements. So he bought, because the simple sunlight is not enough, it was not giving him enough of this violet light intensity. So what he did is that he basically bought a telescope, 7-inch telescope, solar telescope, and all the sunlight he concentrated at the telescope focal plane, and he used those to see this Raman effect, and then it was much better. And then, of course, by 1940s, there were these ultraviolet lamps were available, and he started using those lamps to improve the detectability of the Raman scattering. And yeah, this is the one which has a laser, the ultraviolet laser here, and light comes in through this, and you can see with the microscope, but the sample is kept somewhere here, and then the scattered light goes and it is detected, this Raman spectra is detected, and then you have this analysis of Raman spectra, then it will tell you what material was there in the sample. So today, these are the kind of instrument, and this goes more than 100,000 US dollars. So okay, so that is about Raman's spectrograph, and as you could see, it was so simple, but at the same time, actually, I had a professor in India when I was working in PRL, and he used to say the instrument was simple, but the detector and computer that is used is unique, and you will not, you can spend any amount of money that you want, but you will not get those detectors and the computer that Raman used, and that is Raman's own eye and his brain. His brain is the computer, and his eye was the detector, and so that is what he used to make joke. This Arvind Bhatnagar, if any of you know, he was the founder director of Udaipur Solar Observatory, where I used to work for some time. Okay, so this is the thing, and then let me now tell you the style of working of Raman. And how at that time he was influenced. He and generation of scientists were influenced by Mahatma Gandhi. I wanted to choose this because these days we hear a lot about Gandhi, Nehru, and all these people who they were all before our time. We don't know much about what was happening, and a lot of people tell various things. And I wanted to find out what people like me, who are the practitioners of science, were thinking about these great men of their time. So, so basically, let us see. So, in the rest of the time that we have for this lecture, now I want to examine. I want to see Gandhiji in Raman's eye. Why? Why? Because this quote I take from Gandhi movie. Any of you, if you have seen Gandhi movie, which was made by Richard David Attenborough, Richard Attenborough in 1982, which got Oscar award. Actually, if you go to Hollywood and see these movies that got Oscar award, and this is written there, Gandhi 1982 in Los Angeles. Actually, you have that in Hollywood. So in that movie, he says that Mahatma Gandhi was not a commander of a great army, nor he was a ruler of vast land. He could boast no scientific achievement. Gandhi didn't have any scientific achievement, nor any artistic gift. Yet men, governments, and dignitaries from all over the world have joined hands today to pay homage on this little man, brown man in the lion cloth, who led his country to freedom. It's a British quote, but that is what he thinks. And all these people, Pope Pius and Archbishop of Canterbury, President Truman, President of the United States, and Chiang Kai-shek from China, and Foreign Minister of Russia, President of France, are among the millions. They were there when Gandhiji's body was taken to for funeral. So all these people were present at the time. And why? Because this guy was not a great, he didn't have any of these, scientific achievement or artistic gift or, nothing. And he was not a good looking, actually, he was an ugly man. So why they were there? And then he concludes that perhaps Mahatma Gandhi had become the spokesman for conscience of mankind. That is why he was so much revered by people of all walks. So, okay, this is a quote from Gandhi movie. So, with all this, I wanted to know what scientists or the practitioners of science, which are more objective than poets or politicians, what were they thinking and why? So this is a quotation which quite often used to describe Gandhi. Generation to come, it may well be will scare belief that such a man with blood and flesh walked upon this earth. Actually, it is true now. If you think of it, by now we have so much misconception about Gandhiji that this Einstein's prediction was true. It is hard to believe that such a person ever existed. And this Einstein says when Gandhi was alive at that time. So if Einstein said like this, Einstein was basically at that time, he was working in the United States. So what happened to what were the scientists that were present in India at that time were thinking? So that I wanted to investigate. And so to do that, this is a little background, context. This timeline gives a bit of context to compare, to understand the views of Raman, how the relationship that he had. So Gandhiji was born in 1969, and by 1969 was actually, I was in 5th standard, and we had Gandhi's centenary. My father was teacher of our school, and he organized, I still remember, a big way in our village. He organized Gandhi centenary, and I gave a talk about Mahatma Gandhi, and I received a prize. I think I got the first prize or something like that. Basically, I by heart some paragraphs and spoke in a gathering in the competition. So that was 1969. But 1869, Gandhi was born, and by 1888, his first son was born, and the same year of C.V. Raman. So you can actually imagine that Raman had a kind of fatherly relation with Mahatma Gandhi. So by 1906, when already Raman had written 2 papers on the scattering of light, and he had actually published in Proceedings of Philosophical Society of England. So at that time, Gandhi had this satyagraha at the Empire Theatre in Johannesburg. So Gandhi had not returned to India. He was working in South Africa, and but he had already this impact of satyagraha in South Africa. But around the same time, Raman also had these great achievements, because these 2 papers that Raman wrote in Proceedings of Philosophical Society, they were so good that Lord Raleigh started communicating with him. He sent letters, and in that he writes Professor Raman. At that time, he was not professor; he was just a student, and his professorship comes much later. Almost 10 years later than this. So Raman had also achievement at such a young age. And Gandhi returns to India in 1915 and gets a hero's welcome in Bombay, and all newspapers had this. And at that time, Raman was doing research in Calcutta. And in 1921, Mahatma Gandhi takes the charge of Indian National Congress in Ahmedabad, and at that time, Gandhi was invited. Gandhi was already Raman was already a professor in Calcutta, and he was invited by J.J. Thomson to give a talk in Oxford University, and he goes to England at that time for the first time. But following years, like 22 to 24, Gandhi starts going to jail, and a series of fasts. Like Gandhi had, there is actually a catalog of Gandhi's fast, sometimes 5 days to 21 days fast. And all these fasts Gandhi does are on moral grounds, not for gaining anything. Like, the first 21-day fast, the 5-day fast was to stop the Chauri Chora incident. You might have already, if you know about Gandhi, you might be knowing that, in Chauri Chora, the people who were agitating for the freedom of India, they killed some policemen, and Gandhi said, stop it, and I don't want any of these things to happen. And then because they did that, and to withdraw his movement, he did 5 days fast. And then anti-violence, he did 21 days fast. So with this, Gandhi was becoming famous all over the world. And around this time, actually, that is another topic, maybe another time I can speak, that Gandhi was nominated for Nobel Prize, but he doesn't get around this time. But anyway, so around this time, Gandhiji becomes very famous worldwide. At the same time, Raman concentrates on his work, of course, and he publishes his paper in 1928 and gets Sir, knighted by Queen in 1930 and gets Nobel Prize. And and later, of course, he joins 1933. He joined Indian Institute of Science in Bangalore. He becomes the director of Indian Institute of Science, and throughout this, not much happens after that. He's continuing his research until he makes the Raman Institute in 1948 and 1954. He gets Bharat Ratna. Before that, of course, during this time, not much happens. Gandhiji becomes more and more famous. And of course, these big things that happen in India, Dandi March, and out of many fasts, this was one of the very impressive fast of 21 days to eradicate untouchability from India. And then, of course, just before his death, he does this Hindu-Muslim unity fast and the during actually on the day of India's independence and before his death again for communal harmony, he does 66 days fast. So these, if you were present at that time when such big things that were happening in a society, obviously you will be influenced, and Raman was no exception. That is why, that's why in Sweden, 1930, when he got Nobel Prize, and this is a Nobel Prize picture, and here is Raman for physics, and for chemistry, Hans Flesser, and Karl Landsteiner for medicine, and for literature, Sinclair Lewis. All these people are there getting the Nobel Prize. And at that time, when United States charged the affairs, he sends a cable to the Secretary of State of United States, and then he writes the following. He says, when Sir Venkat Raman wearing a turban, he was the only non-white among these okay, let me. Yeah, he was the only non-white. Sir Venkat Raman, he gets this sea of white man and only one brown person. And in his speech, which was a masterpiece and eloquence, but he concludes in his speech with the British ambassador who was sitting next to this Charles the Affairs of United States. He will be less appreciative because Sir C.V. Raman mentioned the congratulatory telegram which he had received from his dearest friend who was now in jail. So, the dearest friend of Asia, the first physics Nobel laureate was a politician, the dearest friend from which he got the congratulatory telegram was a politician, and he was Mohandas Karamchand Gandhi. And in his Nobel lecture, he mentions that that is the most precious thing that he got. And then he says that the British ambassador who was sitting next to him might be less appreciative because, they thought Gandhiji is not British admirer. Of course, he was not. So, so that was so that shows the greatest respect that Raman had for Mahatma Gandhi, because in his Nobel lecture, he mentions that the most precious thing that he got was the congratulatory telegram from his dearest friend who was in jail at the time. And then, of course, Gandhiji, all this rest of the things happened and Gandhi was assassinated. So we are able to now get another glimpse of opinion or of Raman about Gandhi. So C.V. Raman says that I was not an active participant in the struggle for political emancipation. Neither did I seek to contradict the the leaders leaders engaged in it. But the Mahatma was so obviously different from anyone that I had ever known that each of the many occasions on which I saw and met or heard him reminded vividly the impression that on my mind, on my memory. Asia has produced other such great humanitarians in the past whose life has left behind a permanent impress on the minds and lives of humanity. Once again, let me say that one cannot anticipate the verdict of history. Nevertheless, it is true that history does occasionally repeat itself, and it may be so in the present present one as well. So this is what Raman says on the death of Mahatma Gandhi. It was, of course, everybody was shocked, but that is what is the thought of course, this is a movie, but oh, maybe we should see this. Yeah, so, you know, when these ashes are...
in full view of the thousands who had traveled all night to pay him their last tribute. Laid on a hastily converted army truck, the body was drawn into the vast crowd lining the roads to the cremation ground. Flames strewed a saffron shower of petals over the roof, while at the funeral pyre, the relatives and friends built mounds of flowers and perfumed spices high on the sandalwood lawns. Nearby with his family sat the Governor General with officials of the government. The flower-decked cortege moved slowly through the dense throng. Tens of thousands wept openly as the body passed by them. Premier Nehru, traveling on the funeral coach with Gandhi's youngest son, appeared bewildered in his depth of grief. Closing behind, pressing forward, came a million mourners. Around the pyre, the throng became packed as the body reached its resting place. Of all the faces in that vast multitude, the most serene was that of the Mahatma. To those around him, Gandhi had seemingly been transformed from a beloved saint into a divinity. Ramdas Gandhi, youngest son of the Mahatma, placed the torch to the pile of sandalwood, and as the first plume of scented smoke lifted above the pyre, the great concourse of mourners swept across the barriers towards it. Against this tremendous human tide, the police were almost powerless. Mourners were forced close to the fiercely burning ghat. But, as in Gandhi's lifetime, peace won where force had failed. The mass hysteria was broken by the chanting of a hymn. Mahatma Gandhi has become immortal. In the rising flames, the spirit of a great man passed to his gods.
So on this occasion, actually, Raman says this. Okay, so this is what, you know, the final thoughts of Raman. But before that, there were a couple of exchanges that happened. 1927, Gandhiji visits Indian Institute of Science, and later, 1936, he visited the Raman Institute. So in this, and you know, Gandhiji had what, in my opinion, the Raman's idea about Gandhi developed, perhaps, was because Gandhi had this practical approach to what science can do to his fellow men. That is, he believed that the problems of the poor and those at the margins of the society should be focused by the scientific research. That was his Gandhiji's emphasis. He viewed technology with suspicion because, at that time, unemployment was large, and basically the technology in Europe, in England particularly, was keeping people in India in poverty. So that's why Gandhiji did not have that taste for the technology. But when you pursue with passion for understanding the basic truth of the nature, that Gandhi did not have much contradiction. So that gave, because in one of the speeches in that visit, in the speeches, Gandhi says that just as some of the experiment in your laboratory go on for all the 24 hours, let the big corner of your heart remain perpetually warm for the benefit of poor millions. So always Gandhi's focus was for poor people. And in his speech, where Raman invites, and you can see this one in this picture. This is Mahatma Gandhi, of course, and this is Sir C.V. Raman, and this is Kasturba Gandhi, and he was the head of the physics department in IISc, and here is Mahadev Bhai Desai, his secretary. So this is a very historic picture in Indian Institute of Science, and there he gives this lecture. I expect for more from you than from ordinary man in the street. Don't be satisfied with having given the little you have done and say, we have done what we could do, and let us now play tennis or billiards. So I tell you, in the billiard room and on the tennis court, think of the big debt that is being piled against you from day to day. Because the money that you are using to do your research comes from these poor people, and you must think about them. Don't be afraid of wearing clothes of poor woman that this poor woman make for you. Don't be afraid of your employers showing you the door if you wear khadi. And I would like you to be man and stand up before the world, firm in your conviction. And the same conviction was there with Raman. So this kind of conviction impressed perhaps C.V. Raman, that he had so great respect for him. And then while doing this research, I came across what was the effect of Gandhi on Chandrasekhar, who got again Nobel Prize in astronomy to discover this white dwarfs, that is the death of sun-like stars. When he was asked, actually this you can see from the American Institute of Physics website, the conversation, there is a live interview of Raman, of Chandrasekhar, who was, Raman was his uncle actually. So the interviewer asks how much you were influenced by the leaders of that time. Then he says that, of course, it was the time of Nehru and Gandhi, and others were active in politics. So all the young men like them, like Chandrasekhar, they were all very much involved and very much influenced by their ideas. It was all, let me read this. It was all very much in the air. And of course, we were, all the young students, all were proud of men like Nehru and Gandhi. And it was a part of patriotism of those times to try and see what Indians could accomplish with respect to the external world. Accomplishment in science was one of the ways of expressing what Indians could do, you see. And I could say that this motive was present, the patriotism. The patriotism is a word which is not very popular these days. But patriotism, as it was understood in India in 1920s, was one in which it was a part of everyone's wish to show that Indians could accomplish. So that was, driving them, motivating them to get them recognized outside the world. And actually, if you see, around the same time, 1931, Chandrasekhar gave this Chandrasekhar limit. Chandrasekhar limit is the limit at which the stars cannot compress any further on their death. So that was the Chandrasekhar limit. In 1920s, around the same time, C.V. Raman gets Nobel Prize. And so in that context, he was saying that all those people like Raman and Chandrasekhar, they were all motivated by the national leaders like Gandhi and Nehru and so on. So this was just to show the other contemporary scientists of India around that time, the influence on them of Gandhiji. This is another very interesting and small story of Gandhi when he visited Raman again in 1936. At that time, today there is in India, we have a lot of this controversy going on, whether Hindi should be a link language or a national language or things like that, Hindi or English. So the same thing, there is a little conversation. Mahatma Gandhi wants to poke and find out what Raman thinks about this. And here is the visit. Here is Mahadev Bhai Desai, and here is Raman following Mahatma Gandhi. This article was published in Horizon in June 6th, 1936. In that article by Mahadev Bhai Desai, who was Gandhiji's secretary at that, all through his life, he writes his recollections of introduction of Gandhi and Raman. And so Gandhi asks, don't you think that, if we make English as our language, then don't you think that it will be bad day for many millions of Indians who know Hindi without learning it, and they would have to know English? So what is your opinion? And Raman, of course, he didn't know Hindi, but at the same time, he says, I know Hindi too, Mahatmaji. I understand it very well. I learned it from no less than a teacher, Pandit Madan Mohan Malavyaji, whose wonderful Hindi I had sometimes to hear for hours when I was in Kashi. And I could not help learning it. So that is how he learned Hindi. But I cannot speak Hindi. It is that concept. So you know that, and I am full as much as you. So, this controversial topic, this was controversial even at that time. And Raman was, South Indian, and he was not, of course, he didn't know Hindi, but look at the tone when Gandhiji asks him, what is your opinion about the language policy of post-independent India? And without any hesitation, Sir C.V. Raman says that, oh, okay, yeah, it should be like that. So this is another occasion where you see Raman's liking for Mahatma Gandhi's opinions. And of course, Raman was very much a Gandhian. And later on, he invites Vinoba Bhave to Raman Institute. And here is a picture of that occasion. And then Nehru. So Nehru is another character of that time with which Raman had a lot of interaction. And unlike Mahatma Gandhi, Raman had a competitive attitude towards Nehru. So he always thought, in my understanding of all the things that that is available in literature, my understanding that Raman always thought wanted to compete with Nehru and show that he's better than him. So this is the occasion when Nehru visited Raman Institute, and he shows his little spectrograph and so on, and introduces students. But he did a very interesting magic. When Nehru enters the room, he switches off the light and then brought a copper plate and a gold plate, and then signs them with ultraviolet light. And then asked Nehru identify which is gold. Of course, which was signing. Nehru told, "Oh, okay, that is gold." But then he laughs loudly and then tells, "Mr. Prime Minister, all that glitters is not gold. This is gold, which is not glittering," with the ultraviolet light, of course. So he wanted to kind of embarrass him, and he just made fun of Nehru. And then, but this quotation he uses several times because he was very critical of Nehru's policies of big science. He wanted small science in the schools and laboratories, and Nehru wanted to accelerate the scientific progress in the country because he wanted to have economic use of science and technology. So that was a difference of opinion, but that is what was the funny occasion that occurred on Nehru's visit. But at the same time, he had a very great respect for Nehru and wanted Nehru to help build the Raman Institute. And Nehru asked during that conversation that, "Raman, why do you worry about the future of your institute? The government will gladly take care of it." Then he says, "Sir, who can predict the fate of politicians and what they say? And I want an unconditional commitment from you now to, support the laboratory and not make Raman Institute as another government laboratory. So you keep a lot of independence and autonomy." And I think now also the Raman Institute maintains that. And but then towards the end of his life, Raman was pretty much disappointed with the development that were going on, and he thought, when he makes this statement sometimes in 1970s before his death, that my life has become an utter failure. And I thought I was the first Asian to bring home the Nobel Prize in the scientific field. I thought I would bring true science in our country, but all we have now is a legion camp for the followers of the West. And many of us, including me, of course, we migrated to West. So there can be no salvation and no advent of science. So science for Raman was to focus on what interests you deeply and not to, be a follower of Western world. So that was what it was. And I want to conclude here that with that statement of Raman, what all today we should strive is to follow Gandhiji's this talesman. So Gandhiji, and so this picture is in the Raman Institute where Raman was cremated. You have a tree there. And as I told you in the beginning, Raman says that I believe only in the spirit, and I have heard of Buddha, godly men like Buddha, Jesus, and all that. But I have seen a man like that, and that is Mahatma Gandhi. So I want to conclude by saying that the way we should practice science, technology, or any other field that we have in our life to bring to a height. And that can only happen if we kind of follow this barometer or a scale or the talisman of Mahatma Gandhi, and that he says, whenever you are in doubt and when the self becomes too much with you, apply this test and recall the face of the poorest and the weakest man whom you may have seen, and ask yourself the thing that you are going to do, whether it will help him. And, if we use this test for ourselves, then the science that we do will be great, will be elevated, and also it will be a unique thing, will not be just a repetition of the Western science. So that is very much needed these days, I thought. And with this spirit of Raman, or that encompasses our original ideas of the land, of people like Mahatma Gandhi, that only can bring us to the originality and will stand in the international stage. Otherwise, it will just be another measurement or a repetition of what Western people do. So I think with this, I'll conclude my talk, and I'll be happy to take questions. Oh, okay.
Thank you so much, sir, for this very wonderful lecture. And you have very well connected all the science and then politics was there. And when in today's time the country is running on this probably that dream of Sir C.V. Raman, and we are now right now we are focusing on the indigenous knowledge and the technology whatever can be developed indigenously in our own country. So there are a few questions from audience, and I'll just take right away because we are already running ahead of the schedule. So the one question is there in Raman effect, why are we getting green color along with violet color after using violet filter? So this question has come from Ishan Pare.
Yeah, so the violet light, which is with the photons are of higher energy, so they incident on a cloud of molecules. Now, then this cloud of molecules absorb that light. Now, two types of scattering by these molecules can happen. One is the elastic scattering, where the energies of these incident photons are not lost. And those photons that you see are violet light. But the other type of scattering is the inelastic scattering. Inelastic scattering means the energy of the incident photon are lost. A part of the energy is lost. And those are these green photons or the green light that you saw. So green light is due to the Raman scattering. The other violet light that is scattered is called the Rayleigh scattering. That is elastic scattering, and this is inelastic scattering. So green light is inelastic scattering, okay, or the Raman scattering.
So there is another question. The advantage of UV lights over other frequencies of light used in Raman spectroscopy.
Yeah, in UV light, when you Raman scattering, the efficiency of Raman scattering is higher in UV light. So that you saw that 1 in 10 to the power 7 photons will be scattered. But if you go to lower and lower wavelengths, or the ultraviolet wavelengths, in this case, the more light will be scattered. So basically, the efficiency of Raman scattering increases as you go to the lower wavelengths.
Okay, so there is one question from Siddharth Dubey. Can you give some more ideas on strain check by Raman spectroscopy using the peak shift? Basically, what he's writing, his question is, how can we do before experiment, which peaks can shift under thermal exposure?
Oh, which peaks can be, yeah, actually this is a little more complicated than the question. Basically, what happens is that Raman scattering, this elastic scattering, or the Raman scattering, it depends on the structure and the thermal properties of the target, that is the cloud of gas or the molecules or the target, the thin film or whatever you have. And it all depends on that and how much thermal exposure or the annealing that you are talking here. That basically will what will happen is when you do a sample to the thermal annealing, more number of atoms or a more number of molecules will be in excited state. So basically what will happen is this, there will be no shift, but those Raman states will have more intensity because by thermal annealing, you are elevating a lot of these molecules to higher excited states. So basically those states will have more intensity in the Raman spectra. I think that is the case.
Yeah, so one more question in his question, he has written basically 3 different questions. So the next one is, can we quantify stress by Raman spectroscopy?
Oh, yes, yeah. When you do this, basically when you give a stress, then what is happening is that the stress distorts these molecules in a particular fashion, and from there you can quantify the stress. And this is used in the graphenes.
Yeah, so he's asking for any good reference for study Raman spectroscopy's applications.
Oh yeah, there are a lot of books. Often I won't have. Maybe if you email me, I'll send you some references.
Okay, so there is one more question that you said in your talk, that only molecules show Raman effect and metals don't do it, but why?
Oh yeah, that is because molecules will have this polarizability capability. That is, these are asymmetric. So electron clouds are asymmetrically distributed around the molecule. And for the metal, these are all a lot of free electrons, and there is no polarizability. That is, you don't have a permanent polarizability or a kind of asymmetry is not introduced. It is all symmetric. So basically then there is no scope for inelastic scattering. That is, when the photon goes to the system, it will there is no asymmetric modes in which it can be absorbed, and the emergent photon will have different from the incident photon. So if there is no difference, then it is elastic scattering, and that is basically Rayleigh scattering.
Okay, so there is one question from Suraj, that experiments of Raman effect should be done in vacuum chamber because there are impurities present which may cause fluorescence and unexpected observations, or is there?
Yeah, it depends on the application. In our case, we do not do in vacuum. We have just a surface, and then you sign it the way I showed in one of these slides, and you can see the Raman effect. But if your sample fluoresces and so on, then of course you have to take those precautions. It depends on the application.
Okay, so there is one very basic question, that what is the significance of having Raman spectra of a material?
Significance of?
Having Raman spectra of a material. Why do we do that?
Significant is that, the significant is the following. When it was discovered, at that time, only the elastic scattering was known, and inelastic scattering was not known. So scientifically, it was very important to consider that at that time, in 1930s, that light is in the form of quanta. So it gave a lot of insight to the quantum mechanics at that time. And of course, now the significance, as I showed you, this host of applications in various fields. So That's the significance of the present time. And at that time, basic physics itself was advanced due to the Raman effect.
Okay, so this will be the last question from this discussion session. So apart from being non-destructive, does Raman spectroscopy have other advantages over the similar techniques?
Oh yeah, you can use very trace amount of materials, very small amount of material uh, to um, to detect what they are, and so that is one. And also, it is very accurate. It is much more accurate than many other techniques, like you have written fluorescence spectroscopy and many other X-ray fluorescence or many other techniques are there, but this is very accurate and very precise, the Raman spectroscopy. So that it's
Okay, so with this we'll conclude today's session. And on behalf of VIT Bhopal, I'll once again thank you, Dr. Debi Prasad Choudhary, for giving your precious time and being a part of this discussion on this auspicious occasion of National Science Day. Thank you so much, sir. Thank you.
Thank you very much, Sharad. Hope to see you sometimes in India.
Yeah, sure, sir.